So I will start presenting them. So this is the topic of my presentation today, uh, acoustic scene analysis with machine learning or neural networks. So let me first start with very basic introduction of what is this problem of acoustic scene analysis. So it is basically analyzing the audio signals, and audio signals, as you know, are of different types. There is speech, like I'm speaking. There is music. Music is also an audio signal, but its characteristics are very different as compared to speech, right? Um, in terms of you want to do statistical analysis, semantic analysis, content analysis, so very different properties. Um, and similarly, we have environmental sounds. Environmental sounds are such as uh, different kinds of sounds in the environment, car noise or door slamming, etc. These are all called, these are all uh, fall in the category of environmental sounds. Now, let me discuss what all things can we do with these audio signals. There is a large variety of things. So first of all, let's discuss speech. For speech, we all know ASR, automatic speech recognition, which essentially means speech to text. If I speak something, the machine or the computer gives me the text corresponding to that speech. That is called ASR. Then we have speaker identification. This tells me who is speaking, identifies the speaker, who is the speaker, whether Mr. A is speaking or Mr. B is speaking, identification. Then we have another area in speech analysis is speaker diarization, which means let's say there is a meeting going on and there are five people sitting in the meeting and they are all speaking in turns. So this speaker diarization is it tells you uh, who spoke when. Like there are, let's say, five people, then person one spoke from this time to this time, then person two spoke from this time to this time, then person five, then person one again in this way. So it tells me who spoke when. This is speaker diarization. So these are some of the popular tasks which we do by analyzing speech uh, mechanically or with machine. Similarly, you come to music signals. You can have music recommendation. You all use YouTube or Amazon Music or Geo Music, Spotify. So these are all, they recommend you a playlist, right? Let's say you go to YouTube, you see you are listening to some music, it will recommend a list of other similar musics which you might like to listen to. So this is called music recommendation. Then music search. I want to find a song. I don't remember the lyrics. I just remember the tune. Can you find the song out? Or you have a recording of that song, maybe which you heard in somewhere and you recorded the audio, but you don't know where is that audio, where is that song actually. So you can search it. Music information retrieval. I want to know what are the instruments playing in the music, who is the singer, what is the singer singing, what are the notes the singer is singing. Can you separate the singer from the background instruments? So all these topics are um, studied under this header of music information retrieval. Then you can have environmental sounds. How do we analyze environmental sounds? There are two popular tasks which I list here. One is called event detection, which means you have, let's say, some event happening. Let's say, and two cars are colliding. This is an event. You want to detect, let's say, you put a sensor in the traffic light and you detect if there is some accident happening, and uh, that will help you to send ambulance or to call police or to send somebody to rescue. Then scene classification. It classifies the acoustic scene, whether I'm sitting in a park or I'm sitting in an office or I'm sitting in a hostel or I'm sitting in a train or a train station, right? Every location has a different audio background, right? So in that kind of audio background, uh, can I estimate where am I sitting, or can the machine tell where am I sitting? This is called scene classification. So there are various examples. Let's say I want to monitor the traffic. If there is a heavy traffic, sounds are very different. Less traffic, sounds are very different. Gunshots, there is some gunshot happens and you can detect it. For example, in the forests, you want to avoid illicit hunting. You can put sensors. Sensors are basically microphones, right? So you put some appropriate microphones in the locations, and then which will be listening to the environment, and any gunshot happens, immediately they will send a notification to the forest officer or the in charge. Then in smart homes, let's say you have a house and you have baby and you want to, let's say you are working in the kitchen and there is a baby in the bedroom and you want to uh, monitor when the baby starts crying, give me a notification. It is there in Alexa. Even today, you can use it. These things are already there. Okay, so these were some of the example problems which are popular around audio analysis in general. And how do we solve these problems automatically? So with the help of machine learning. And if you ask me in one sentence, what is machine learning? So I would say, okay, there is a model which transforms the input to the output. That is machine learning. Oh, this is a very simple definition, but just very good first approximation or first hand understanding of machine learning. So let's say in audio, the input could be the audio waveform or some processing of audio waveform. You extract the spectrum or some features from the audio waveform, and this is your input. What is the output? Depending on the task, your outputs will be different. For example, you want to do speech recognition, then the output is the text. You want to do sound classification, the outputs are the categories or the classes or the labels which you want to detect. And the model is the main part, that how exactly do you learn this mapping given the data, given the training data. You want to learn the mapping. You can define this mapping simply with the help of rules also, right? People have been doing it for many decades now. But um, but that kind of handmade rules, they have their limitations, severe limitations, and they fail in with a slight change um, in the environment or in the quality of the sound which we want to analyze. But if we use machine learning, then we can learn statistically from the data that what should be the robust model which maps my input to the output very reliably. So let's have a look in terms of audio analysis. What is my input? My inputs, uh, how do I measure sound? I measure sound with the help of a microphone. My microphone will record the audio and it will give me a waveform. This waveform is an analog waveform, basically, which is the voltage fluctuations in the coil. And then I digitize this audio. How do I digitize? We basically sample it in time, and we also digitize it in uh, we do the um, we did it's called the amplitude. The amplitude also is discretized, or it's digitized, and then we save those values into my array, and that is called a waveform. So a waveform is essentially a stream of numbers. Now, this stream of numbers I can use as it is. I can feed this into my model. Remember this figure that there is an input, output, and then there's a model. So what I feed into my model, it could be this raw audio waveform, but is it a good representation? Um, yeah, it is complete representation. It contains all the information, but maybe it contains a lot of redundancy also. And that much redundancy will cause a problem in my model, because my model will have to deal with so much of data. So why don't I reduce the redundancy in my input dimension, in my input? That can be done by extracting some useful features out of my input signal. And the quality of this feature, whatever I extract, it should have these qualities. One, it should be low dimensional, as small as I can make, as compact as I can make, but discriminating for YT, which means without losing the information which I want to extract from it finally. Low dimensional representation. And then invariants. So there could be many redundant factors, or there could be many non-useful factors. Let's say if I want to do speech recognition, I may not be interested in the pitch of the sound. I may not be interested in whether the person is singing or just speaking. I'm just interested to know what is the phonemic content or the linguistic content in the speech. So I will use a kind of features which ignore the pitch information from the input. So that's the feature extraction part. And this is the generally how we extract features from the speech waveform, let's say, or any audio waveform. You have the audio waveform, it's a long sequence, and I can't feed whole thing into my system. So what I do, I take small windows out of it. They're called time frames. I take small frames, and these frames are overlapping, as you can see here. They could be overlapping. And why do we want to keep them overlapping? So that we don't miss any information. So we have these overlapping frames, and from each frame we do some analysis and extract some features. So of course, if I feed the entire frame into my model, that will be also a valid thing, but then the redundancy will be there. So that's why I extract some acoustic features which I think will be useful, and then I will be working with them. So generally, we do a Fourier analysis on my time frame. I extract the frame and I perform a Fourier analysis. From the Fourier analysis, I extract a spectrum for this frame. And for that spectrum, I ignore the phase part. I keep the magnitude part only. Remember, the spectrum is a complex number, so I ignore the phase part. I just keep the magnitude part. And by that, I uh, I get a spectral representation. Now this spectral representation can be further compressed with the help of filter banks. So in simple words, what are filter banks? They measure the energy in different bands of my spectrum. What is energy? It's basically the amplitude square summed over all the winds, or summed over the frequency axis. So this is the notion of energy in my spectrum. And I extract energy components in different bands, which means different frequency ranges. Again, these ranges could be overlapping. And in this way, I extract a set of numbers. So all these things are pretty standard, and there are toolboxes or libraries available to do all these things. They're very classical kind of things, so we don't spend much time here. Let's go to the next part. So once we have obtained the features, now what do I want to do with my features? I want to map them to the output. Input is done, now output. What is there in my output? Now, depending on my problem, my output could be different. For example, I want to detect uh, oh, um, I want to detect the start time and end time of my audio. Let's say I do I want to detect a sound, let's say a clapping sound. So I want to also detect when did the clapping start, when did the clapping end. I want to detect beginning time and end time also. Then I will do a frame level analysis. So basically my output will be uh, at frame level, that what is the input time, what is the output time, even that will be known. But I could do a more general analysis depending on my problem. That could be stream level analysis. And the example could be acoustic scene classification, right? Whether I'm sitting in the office, or I'm sitting in the park, or I'm sitting in a train or a bus. So, so basically I have to just classify the whole audio into one category, whether it's park or bus or train or office. This is called stream level analysis. And another level of analysis could be segment level analysis, where I want to detect start time or end time, but they are not very finely tuned. They could be coarse also. Okay, let's say uh, for 5 minutes I'm speaking, and then for 10 minutes I'm not speaking. So which means that my boundaries of detection could be very coarse also. So this is called segment level analysis, and each segment could be of length, let's say 5 seconds or 10 seconds or even half a second. So I can choose what is the length of my segment, but essentially that will give me a coarser analysis of my start times and end times. So depending on my requirement, I can choose any of these three modalities of my output. Now coming to the main part, how do we make the model? How do we make this mapping from input to output? And the popular ways are linear classification, right? So linear classification just means my output is what do you say, weighted sum of my input feature, and these weights are parameters of my model which can be tuned to give a good output. So these are called linear models, right? My model is linear with respect to the weights or the parameters of the model. Then I could have probabilistic models. Probabilistic models, as you know, there are uh, probabilis- uh, there are ways to model probabilistic distributions, probability distributions. For example, Gaussian mixture model or Poisson model. And using these probability distributions, I can take a classifier or a detector which can detect my sounds or classify my sounds. Similarly, I can have support vector machine, and recently neural networks have become popular. So there are different kinds of models possible. And today in our discussion, I'll be focusing mostly on neural networks part because this is state of the art and very popularly used these days. So I will start with one simple video to tell the. Now we discussed the overall problem of audio analysis. Now, what are the applications of this problem, and what is the current uh, commercial value, or you can say in terms of industry, how far people have reached? So there is a short video. This is on Amazon Alexa, and especially a feature in Alexa called Alexa Guard, which listens to the sounds in the house and detects if somebody has entered the house without your permission. So I was working in this project. This whole project was built by my team. Um, and so I will just present this. Am I audible? Is this audible?
Yes, sir. Yes, sir.
Just wanted to know if the sound is also
Yes, sir.
audible.
Yes, yes.
I can't hear.
You are audible. You are very well audible.
Yes. Okay.
Can you hear us?
Guard is a new Alexa feature that helps you keep your home and family safe. When you leave, set Guard to away mode by saying, Alexa, I'm leaving. Once in away mode, your Echo device can detect the sounds of smoke alarms, carbon monoxide alarms, and glass breaking. If one of these sounds is detected, Alexa can let you know with a smart alert via phone notification. You can listen to a 10-second audio clip of the detected sound in the Alexa app, or drop in on your Echo remotely to investigate what's happening in your home. Guard works with security systems from Ring and ADT. Alexa can arm your system when you set Guard to away mode. And with professional monitoring, you can forward smart alerts to your security service provider. If you have connected smart lights, Alexa can control them when Guard is in away mode to make it look like someone's home. To set up Guard, open the latest version of the Alexa app on your mobile device, go to Settings, and select Guard. From there, follow the simple step-by-step instructions. Next time you head out, tell Alexa you're leaving to put her on guard.
Yeah. Thank you. So this is one of the applications like in smart home, how people are using uh, this kind of technologies. Now another application is, let's say you have a small baby at home and you want to monitor whether he's or she's crying or not. And you put the Alexa in the room, and you can be in the kitchen or in some other room, and whenever the baby starts crying, the Alexa can give you a notification that the baby is crying. So, and similarly, in various smart home applications, let's say, yeah, so more and more things are coming up, and people are using audio analysis for such applications for home monitoring. Another application is in forests or in monitoring the forest life. So uh, there are many forests where, and there are many species of birds in the forest, and somebody wants to monitor how do these species respond to different changes in the environment. For example, as we know, pollution is increasing, uh, global warming is increasing, and this everything has an effect on animal life or the bird's life. Now people want to know how the birds are responding to this environment chaos because of pollution, because of cell phones, or so many reasons could be there. But they want to analyze, okay, how birds are behaving. So instead of putting cameras, because which are very difficult, because where you don't know where are the birds, but a very good way to monitor the birds is just listen to them. So you install microphones in the forest or in the trees, and whenever the birds are coming, you can there can be automatic systems to monitor their activity, whether it is to detect what birds are there or to study their behavior. And such applications are also used in controlled environments to study how birds they behave, because birds also have some language, some primitive form of language, and to study that how do birds, so people do behavioral research on birds using such technologies. Another application could be in industry, where there are so many machines are running, and you want to find out if some machine is at fault. How do we detect? How do we detect fault in a machine? By listening to it. When the machine, let's say there are some rotating parts in the machine, and whenever there is a fault or something, you will hear strange kind of noise. So people who are machine operators, they can just by hearing, they can tell the machine has some fault. So why not we make a machine or a smart machine learning system which can detect such faults, and using that, then there can be monitoring done for large at a large scale. So basically, machine learning, it helps you to scale up everything. So just like in a small factory, you can have people who can listen to the machines, but let's say in huge factories or in huge setup or in distributed factories, you cannot send people everywhere. So just put such machines. Um, and uh, such areas are also there is active research happening in these areas, and there is a popular annual challenge called DK's challenge, which happens every year. And they also have a workshop and a challenge. They have different tasks every year. The list of tasks gets updated, and they do every year, and people participate and they submit their models to do the tasks, to classify things or detect different sounds, etc. And this is a popular, so basically I mean to say that this is a very popular area of research, and active research is happening. Okay, now with that I can come to some technicalities of this problem. So let me Um, so let's say, what are the possible problems? I will just give a little bit, I will enter the mathematics now. So acoustic scene analysis, this happens at the stream level, which means I'm sitting in a park or I'm sitting in a office. So this is a stream level task. You have a stream of audio and you want to classify the entire stream into one class. Then we can have audio event detection, where I could have events which are either overlapping or non-overlapping. Let's say something is very rare, let's say gunshot versus what do you say, an accident. These all events are very rare, so there is very less chance that they will overlap. But okay, so there could be non-overlapping events, but there could also be overlapping events. For example, traffic noise versus somebody speaking. They can be overlapping. So speech and traffic noise, they could be overlapping events. So depending on my problem, I can define my uh, model. So segment level analysis, which means I don't give precise start and end times, but rather just tell that, okay, in this entire segment of 5 seconds or 10 seconds, these sounds are present. Whereas in event level labels, we have precise start times and end times also estimated. Okay, so for this particular talk, I thought I will be talking about segment level labeling only. Segment level labeling means I have a segment of, let's say, 5 seconds or 10 seconds, and I want to classify this segment or label this segment, what all classes are present in this particular segment. So this presentation is based on my work at Amazon, which is called Deep Embeddings for Rare Audio Event Detection with Imbalanced Data. So first I will introduce the problem, the basic problem, and then I will tell about the challenge which comes because of imbalanced data. So in the basic problem, we have got acoustic features, which are it could be spectral features. So what I did in this work is each audio segment was of 10 seconds duration. And let's say I is the index of the audio segment, and xi, let's say x is a matrix, and ith matrix, which is extracted from this audio. Now, how do we extract this matrix? So from audio waveform, we extract 64-dimensional log mel filter bank energy features. And these features are extracted with, you remember the frame size was there. So each frame is 25 milliseconds and the hop size is 10 milliseconds, means the frame advances by 10 milliseconds every time. So this is called LFB features. And then we perform feature normalization using mean and variance. So basically, I have got a matrix. I will make sure that the mean of this matrix is 0 and the variance is 1. How do I make sure that? I just every element you subtract the mean. The mean of the matrix is subtracted from the entire matrix, so the mean becomes 0, and then you divide it by the standard deviation of the matrix, and that makes the variance equal to 1 or standard deviation equal to 1. So in this way, these are very standard steps, and there are standard libraries to do these things. For example, extracting the features, you can get audio libraries which can extract the features from your audio file in Python or whichever language you are using. And then for feature normalization is a very simple mathematical step. So this is how we prepare our inputs to the model. Now let's come to the output. So for this particular problem, we know that there is a single label for the entire audio. So for the ith audio segment, you have a single label called L, and this single label could be one of capital L labels. Now you may ask, can it not have multiple labels? The answer is yes, it can have multiple labels also. So it can have two, three labels also present. So in this particular problem, I am allowing to have more labels also. Okay, now let's come to the model. What is my model? My model is a neural network. That's what I used. It could be a deep neural network, or it could be an LSTM, or it could be a CNN. So LSTM has a memory. It's a recurrent neural network. It has a memory, long short-term memory networks. And CNN, it doesn't have a memory, but it has a property called translational invariance. So you have a kernel or a kind of weight matrix, which you multiply with your input, and you scan your input just like you do for an image. You scan the input with your weight matrix, and this is this format is known as convolution, or this operation is called convolution. And convolutional neural networks, they perform such operations with different kernels, and it would be done in multiple layers. The first layer will scan the input and then gives an output, and this output is again scanned by another layer of another set of kernels, and you get another output. That output will be scanned by another set of kernels, and you get another output. In this way, CNN performs its action. And then in the final layer, so when you do this, all these operations, whether DNN, LSTM, or CNN, you get something. And then finally, you flatten the whole thing. Flatten means, let's say it's a matrix or it's a block. You just straighten it up and you say it's just a vector. And then you feed this into a dense layer or a simple multi-layer. Dense layer is simple. Fully connected layer, and then you get it. The output layer has got a fixed number of neurons, and in this case, it is equal to capital L number of neurons, and capital L is the number of labels. Right? And then I have to put a non-linearity so that my output is confined to the range of 0, 1, because my output represents probability of label L given xi. So So my output represents this probability value. And probability values always lie between 0 to 1. So therefore, we put a sigmoid nonlinearity so that it is confined to the range of 0. And then we use the loss function, which is called binary cross entropy loss, which is this. It looks complicated, but I will explain it so that you can appreciate the mathematics behind it. So what is T? T is the ground truth value or the target value. What is Y? Y is the estimated value, the value which is estimated by our neural network. And I is the index of the audio file, and L is the label index. It could be, let me call it as YI, because that's the convention I have used. Probability of yi given xi. So yi is the output. YIL. No, I think it was correct. It should be li only. Label and then xi. Okay. So this is what we finally get. Okay, now let's say this. Okay, so let's first discuss what is a loss function. A loss function will have a large value if my network is not doing very well, and it has a very small value if my network is doing very well, which means if my outputs are equal to what I actually want them to be, then I have a small loss. But if my outputs are different from what I actually want them to be, then it is a large loss. So let's take an example. Let's assume the case when my target value is equal to 1, which means that label is actually present in the audio. For example, clapping. Let's say the clapping is equal to 1. Now let's say what is my y? My y is the estimate from the network. My network estimates a 0, let's say, or a value which is very small. It cannot be exactly 0, but let's say 0.1, which is very small as compared to 1. So let's say here, if you look at this term, t is equal to 1, and yi is very small, let's say 0.01 something. And this term, 1 minus ti is 1, so this term goes away, it becomes 0, and this term stays. This is log of 1 is almost 0. So let's ignore this part. Only this part becomes active. Now here, yi is 0.01, so which means log of this will be equal to minus 2. So my loss becomes equal to plus 2, because there's a negative sign here. So the loss becomes equal to plus 2, right? So if I make a mistake, which means yi is equal to 0.01, this implies my loss will be equal to almost 2. Now let's consider the case when my yi is actually very large. Yi is approximately 0.01 If my y is 0.99, so what will happen? This is ti is 1, log of this is almost log of 1, which is approximately 0. So my loss will be approximately equal to 0. Right? So this means this loss function is designed in a way so that it gives a large value when my output does not match my ground truth. T is the ground truth. Ground truth means the actual value which some human has told, or somehow you know the right value. That is the ground truth. So when my estimated value is equal to the ground truth, loss has a very small value. When my estimated value is different from the ground truth, then my loss is very large. That's the basic principle of loss function. And this is the binary cross entropy loss. Now, okay, so in this way, now how do I train my network? To train my neural network, I define my network as an LSTM or DNN or CNN, and then I define this loss function in this way, and then I use some optimization techniques to minimize this loss function. Now the crux is that this network is differentiable, or you can say this loss function is differentiable with respect to the parameters of these networks. So now see this YIL, this is a function of what? It's a function of the network parameter. It's a function of the input, right? Input xi, as well as the network parameters theta. So it's a function of both the input as well as the network parameters. And this thing is differentiable with respect to theta. So using these derivatives, you can optimize the network. Right? When you know the derivatives, you know, okay, this is the direction in which if I change my theta, my loss will decrease. So keep moving in that direction, and so that loss keeps decreasing. So this is the basic philosophy of optimizing the neural network. Now, okay, so I got some neural network. How do I evaluate whether my network is good or bad? The answer is you use some evaluation metrics which can quantify how good or bad is your network. Now, these metrics also have to be defined by you carefully so that they make sense. Not every metric is useful for every task. Some metrics may be more appropriate for certain tasks. So one metric which I have shown here is the confusion matrix. This is something called a confusion matrix for two classes, positive class and negative class. If you have more number of classes, you can make more columns and more rows. So what is a confusion matrix? In the rows, you have actual values or the ground truth values. So you have ground truth here and the estimation here, estimated values here. So the ground truth values are here, estimated values are here. Let's say the actual value is the clapping is present, positive, and my network or my model also says it is present. So I will increase 1 here. And when my actual value is positive, means actually clapping is present, but my network fails to detect it, then this will fall in this category. So I will increase 1 here. So let's say finally you have, let's say 100 audio recordings, and out of which, let's say 50 actually had clapping, and 50 actually had clapping, and 50 actually didn't have clapping, for clapping. And out of these 50, let's say 30 were correctly detected by the algorithm, that yes, 30 means the network also said yes, they are present. And for 20, it failed to detect that actually they are present. And out of these 50, for 40 of them, it said, yes, they are not present. But for 10 of them, my network incorrectly predicted that they are present. So this will be my confusion matrix. Right? So this means out of 50 actual clapping sounds, my network is able to detect only 30. and for 50 where there was no clapping, my network 10 times incorrectly said that there is a clapping present. So my network raised my hand, yeah, clapping is present. Here, clapping is not present. Okay, so now using this confusion matrix it gives you the complete picture, but this can be very large. Let's say you have 10 classes, then it will be 10 cross 10, so 100 numbers, and you want a compact metric. So generally we define something called false alarm rate, miss rate. There are other things also like precision, recall, F measure or F1 value, or accuracy. All these metrics are possible, but I'm just discussing these metrics now here. False alarm rate, which is how many times the network gave a false alarm that clapping is present, whereas clapping was not present. And similarly, for miss rate will tell me how many times the network missed the clapping sound. Means actually the clapping sound was present, but my model said it is not present, so it missed the sound. So this is these are the evaluation metrics. Now using this false accept rate and miss rate, I can make a curve. How I can make a curve? Because I have a threshold. Let's say you remember my values can be between 0 to 1. Right? My output can be between 0 to 1. This is my YIL. My YIL can be between 0 to 1. It's probability value of the event being present or not. If I make my threshold very stringent, I will say, okay, to be able to, means my network detects an audio as a clapping sound only when my YIL is large than 0.9. This is a very stingy threshold, which means if my network has a slight confusion, maybe this is a clapping or not, then my YIL will lie somewhere here, but my final threshold will say, no, I will not accept it as a clapping because your confidence is very low or your probability is very low. So only very few will be actually accepted and mostly will be rejected. But if I make a very loose threshold, if I say, if my YIL is more than 0.1, then I accept it as a clapping sound. Or my network raises a hand, yes, this was a clapping sound. Then I will get a lot of false alarms, right? Like even if there is some other kind of sound happening and my network is estimating some very low value, but because threshold is so low that will be counted as a clapping sound. So then my false alarm rate will be very high. So this threshold can make a difference in my curve. Basically, not curve, but based on my threshold, my FAR and MR will change. If I make it too stingy, I will get very less false alarm rate, but very large miss rate. So here miss rate is high. Right? My miss rate will be large. And here my false alarm rate will be large, because my boundaries so loose that everything gets accepted as an alarm or as a clapping sound. So there is a trade-off between false alarm and miss rate. That's why I get a curve by varying the threshold. So this is called the detection error trade-off curve. And there is certain value where both of them are equal, right? FAR and MR are equal. So basically there is a, let's say around here, if you draw a boundary, this 45 degrees line, this is a 45 degrees line where both are equal. So this is called equal error rate. So for this particular algorithm, this is my equal error rate. This point, this is the equal error rate. This value will, let's say 19 or something. So here my EER, equal error rate, is equal to 19. So in this way, I can quantify my matrix, that how good or bad is my algorithm. Okay. So just a kind of an extra thing I want to tell here. Equal error rate may not be the best metric all the time, because you may require a very small false alarm rate. So then you will not be keeping your threshold somewhere here. You will keep your threshold if you want to keep let's say this is the false alarm rate. If you want to keep your false alarm rate very small, then you will be operating somewhere here. So that false alarm rate can be low, even if miss rate is little high. You may not operate at EER, but at some other point. Okay. So with this, we have come to an end to the basic concepts required in audio event detection. Now I'm going to start the next topic, which is little advanced in the sense that this problem is of data imbalance. But before I move to that, I would like to ask if there are any questions. Are there any questions at this point?
So, I want to ask one.
Somehow I'm not able to hear.
So, whether I'm not audible to you? Hello? You can't hear us? Okay.
Oh, I'm sorry. There was some problem with the microphone. Now I can hear you. You can also hear me, hopefully.
Yes, sir. So, can you hear me?
Yes, please.
Sir, yeah, we got one question. Sir, Dr. Hari Murugan is asking about, can you elaborate on EER of 19? What does the 19 indicates?
Okay. Let me go back to my slides. Okay, so this is my false acceptance rate. This is my miss rate. I don't remember exactly which axis was FAR, but just assume this is the one. And I can tune my threshold to any of these values, right? If I make my threshold very large, which means my threshold is very stingy, it does not accept even a high YIL as the detection.